Okay, so kinetic energy graphs dealt with the movement and the temperature of a sample, of a reaction sample, okay, whereas potential energy graphs deal with the amount of heat that was either gained or lost by the system. So if we consider the reaction, and quite honestly these are easier to grasp, okay, we've been talking about them all year. If you consider the reaction A plus B yields C plus D, we know that the energy, the potential energy of the reactants is 40 kilojoules. How do we know that? Well, it shows it here on the graph. Excuse me. Okay, so it's shown here on the graph. Here are the reactants, and here are the products. And let's look and see what happens here before we answer any questions. The reactants start with 40 kilojoules of potential energy, and the products end up with 20 joules of potential energy. So what happened there? Energy was lost, right? It went from 40 to 20 kilojoules per mole. So just looking at this, we can figure out that, well, this is an exothermic reaction. It lost energy. Where did that energy go? It went out into the surroundings somewhere. Okay, so we know that the energy of the reactants is 40 and the energy of products is 20. We could create a potential energy graph like this. Considering only the beginning and ending, this change is exothermic. We called the change in heat energy Q. Yeah, if you recall the first semester, Q equals mc delta T. Well, now we're going to call it delta H. The delta H is always the final potential energy minus the initial. What is the value of the delta H for this reaction? So let's look at it. We go from 40 down to 20. That's your delta H right there. Okay, so what's the delta H? It's negative 20. That's your delta H. Delta H equals negative 20. Kilojoules. Fill in this chart by circling the correct choices. Exothermic goes, well, let's look and see. Exothermic goes downhill. Yeah, it goes uphill for a little bit, but remember what the uphill is. Uphill is adding energy into the system, then you hit this tipping point right there. Okay, you hit that tipping point, and then it goes downhill. Okay, adding energy, and then you reach a tipping point, and then the reaction starts. Okay, so exothermic goes downhill. It's negative delta H, and the products have less energy than the reactants. So here are products. Let's label that in case you've forgotten. These are the products. These are the reactants. Oops. Okay. An endothermic graph is going to go uphill. The delta H is going to be positive, and the products are going to have more energy than the reactants. I'll do it, since we don't have one here, let me just draw one. Here's what an endothermic reaction is going to look like. Okay, it'll look like this. Okay, A plus B, C plus D. This is endothermic. Why? Because C and D end up higher with more potential energy than what you started with. You put all this energy into the system, and then you got C and D with more potential energy. Okay, that's an endothermic reaction. There is an energy hill between the reactants and products. This is called the transition state. The energy of this transition state is, well, this is what they're talking about. This is your transition state. Oops, that should be a T. Okay, that's right when A and B starts to form C and D, is right at that point called the transition state. And where is it at? In this case, it's at 100 kilojoules. Oops, let me do that, sorry. Okay, go ahead and copy that. In this case, it's at 100 kilojoules. How much energy does it take to get from the reactants to the transition state? Well, let's see. Don't say 100 kilojoules because you didn't take into account where we started. Okay, you didn't take into account where we started. Oops, there goes my lights. Hold on. Okay. Right here, this amount right here, the measure of this hill here. Okay, look right here. This is called E sub A. That's your activation energy. This right here. That's your activation energy. That's how much energy you have to put into this system to get it to go, to move forward. Okay? And in this case, you start at 40 to 60, that's 20, 60 to 80, that's 40, and then another 20 to 80 to 100, that's 60. So how much energy do you have to put in there? 60 kilojoules of energy to get this reaction to start. That's your activation energy. Summarized by filling in the following energy values. So the reactants start with 40 kilojoules of potential energy. The products end with 20. The transition state is at 100 kilojoules. That's your transition state right there. Okay, don't confuse it with your activation energy. That's your transition state. And what is that transition state again? The point where A plus B starts to combine and form C and D. Your activation energy is going to be this difference here from 40 to 100, which is 60, and your delta H of your reaction is going to be negative 20 kilojoules. Or in this case, you don't have to put the negative, you can just say 20. You know what, let's put the negative 20. That's your heat of reaction. Okay, your delta H is negative 20. Okay, when the temperature is increased, the potential energy graph stays the same. However, blank, more or less particles are colliding with enough energy to overcome the activation energy. Well, if you're increasing temperature, more particles are colliding. Okay, and that's why you have these two separate graphs here. Okay, because look, this doesn't take temperature into account. In other words, it doesn't take the increase in temperature into account. All this tells you is how much energy is needed for this reaction to start, what you start with and what you finish with. It doesn't take into account how the motion of the particles, how many particles are moving at any given temperature. That's where you use this thing right there. Okay. However, more particles are colliding with enough energy to overcome the activation energy, so the reaction goes faster. It still goes faster. When a catalyst is added, this is a transition state with, when a catalyst is added, hold on, let me pause and try to figure this out, what they're saying. Okay, there seems to be a typo in this thing here. So basically, this is what they're saying. I don't want to keep adding more stuff. Well, maybe I should. You know what? If you add a catalyst to this thing right here, what happens to the activation energy? It gets lowered. But your final points, A and B here, your starting point and your finish point, the amount of energy that they start with and they finish with stays the same. So let me see if I can illustrate that. Let's go ahead and do this. This is with a catalyst. I'm going to add a catalyst. Okay, so the only thing that changes with a catalyst is not your delta H of the reaction. You're still going to lose 20 kilojoules of energy, okay, after you add a catalyst. The only thing that changes is the amount of energy required to get this reaction started. So in other words, your activation energy, okay, and your transition state is going to change as well. Okay, so you're adding a catalyst will lower both of those, but your final points in terms of A and B and C and D where they're at does not change. Your delta H of the reaction does not change. Okay, so when a catalyst is added, and you guys should do this if you can. Here, let me just go ahead and do this. We'll just say added catalyst. Okay. So that's after you add a catalyst. So when a catalyst is added, the transition state is lower. Okay, so when a catalyst is added, the transition state is lower. So more particles can overcome the activation energy easier, speeding up the reaction. The energy of the reactants and products stays the same. Sketch the graph above to show what happens when a catalyst is added. Okay, we're not going to say by 20 kilojoules because I didn't do that exactly right at 20. I should have drawn it up there. But we'll just say that's after a catalyst is added. Okay, that's after a catalyst is added there. That's what it looks like.